sections 8, 7, 8, 8 in calculus, we're starting to get into volumes of shapes and what we can use with calculus to find those. Before we get into volume, though, we need to talk a little bit about area. And let's see what we can remember about these. What is the formula for the area of a square if each side has a length of x? Quick turn to your partner, 3 seconds max. What is the area of a square? Go. It is called a square because you take the side and square it. Great. And then the next one, what if you have a square, but instead of having each side x, you have this diagonal, which has the length of x? Then what would be the area of that square? Now, when this diagonal is drawn, it creates 2 triangles. It creates 2 right triangles. It creates 2 45, 45, 90 triangles even. In a 45, 45, 90 triangle, the hypotenuse is the biggest. So to go to the leg, you get smaller. What do we have to divide that by? Root 2. And this is x over root 2 also. If I wanted to, I could use cosine of 45 equals this over x. I know the cosine of 45 is root 2 over 2. Solve the proportion. I still would get those 2 values. So now if the diagonal is x, that means each side of the square is equal to this. What would you do with those 2 lengths then to ultimately find the area? Wouldn't you multiply them? X times x is x squared. Root 2 times root 2 is 2. So if the diagonal is x, then this would be the area of the square we're talking about. Number 3, how would you find the area of a semicircle? Ooh, didn't like that one. How would you find the area of a semicircle if it has a radius of x? Semicircle is half of a circle. If it was a full circle, wouldn't it be pi times x squared? But it's a semicircle, so what do we have to do with that? Divide by 2. So lots of like little variations on formulas we have to get into. The next one is a semicircle also. And this time the diameter is x. I'm going to slow down a little bit on this one. What would the area for this semicircle be then? Definitely a pi in it. Pi times, what is the radius now? X over 2. So pi times this radius squared. And it's still a semicircle, so we still have to divide it by 2, right? Now, if we simplify all this, square your numerator, that becomes x squared over 4. What is x squared over 4 over 2? Wouldn't it be x squared over 8? So we have pi x squared over 8 for the area of this semicircle. Number 5, I'm saying skip the equilateral triangle with sides of x. Number 6, though, if you have an isosceles right triangle, also known as a 45, 45, 90, the legs are length x, then what is the area? 1/2 base times height. 1/2 x times x, so x squared over 2. Knowing our area formulas and knowing how to use them depending on, are these lengths x, are they y, is this 2x, 3x, small little variations to find those areas is going to be significant for us. Question number 1. Which of stack of CDs has the larger volume? We've got the stack on the left, the stack on the right. Now, the CDs are the same, right? The CD cases are the same. Anybody own any CDs, like with the cases and everything? Okay. The cases are the same left to right, and it looks like they have the same number of cases in them. Which stack has the larger volume? What What do we think? It's going to be the same. Each CD case has the same volume, whether or not you have them going straight up and down or you tilt them to the side a little bit. These are going to have exactly the same volume. Hello Kitty example to the right. We have these poker chips. One of them is really curvy. One is straight up and down. The other pile is just tilting to the side. Which of those stacks has the largest volume? Once again, it's the same. They all have the same perpendicular height to them. They all have the exact same area of their base. They're all going to give us exactly the same volume. How could we estimate the volume of each stack of chips? I don't have chips, I have quarters. So it's a lot smaller. Now, what kind of shape would you classify a quarter as? Like geometrically, what shape is it? Technically, it's a cylinder, right? Because it does have a little bit of thickness to it. If I can make it thinner and a lot thinner and a lot thinner, and I ask that same question again, and some of you answered it this way this time, it's kind of a circle though too, right? Because it's so thin. I mean, truthfully, yes, it is a cylinder because it has a height to it. But the circle by itself doesn't have any volume, it just has area. But if I take one ultra thin quarter, stack another one on top of it, and another, and another, and another, eventually we get a pile like this. And if I asked you, what kind of shape does this represent? Would you have said circle? Would cylinder have been your answer right away? And if I said to find the volume of this one, maybe you have some formulas memorized. The volume of a circle is, or volume of a cylinder is pi r squared, because that's the area of the space times the height. That's how we get the idea, the concept of volume. You find the area of the base, you multiply it by the height because you have all of these same shapes stacked on top of each other. So how could we estimate the volume of each stack of chips? I would say find the area of one of those circular bases and then multiply that by the height. Next question. Does our approximation method, this idea, really this concept of how to find the volume of a cylinder, does it work for a rectangular solid? So we had these CDs stacked up with each other. Is that idea the same? To find the volume for a rectangular prism like this one on the left, is that also going to be the area of the base stacked up or multiplied by the height? Absolutely it is. So in general, it's going to be the area of the base, capital B, times the height. And that is our concept that's huge in this section. We've been talking about finding a lot of areas. For area, you take the representative rectangle, you move it across the region, you add all of those rectangular areas together to get the total area. For the shapes we're talking about now, you find the area of a base and you multiply it by the height of the base. You're dragging it along an axis. Number one, a right cylinder is formed. Now the term a right cylinder, right as opposed to oblique. Right means perpendicular. We are stacking it straight up and down like this one. This would be a right cylinder, as opposed to an oblique and oblique, where it tilts to the side. Your oblique muscles are on the sides. When you like bend to the side, you're using your obliques. This first one here would be another right cylinder. I know it's a prism, but we're going to use a general term cylinder for these. And then when it's tilted, again, it would be oblique, like this second one here. So a right cylinder is formed when a kidney-shaped region, something like this, kind of a random shape, with an area of 22 centimeters, is translated 10 centimeters along an axis perpendicular to the region. So I have this, and imagine that we drag it this way, and we're carving out a three-dimensional shape for a distance of 10 centimeters. So we're dragging it. I'm going to get a little cross section in here until we get all the way to the side, 10 centimeters to the right. And now I have this three-dimensional shape. My drawings aren't the best, but can you kind of picture that as a 3D shape? We have like this shaded in part here. Could be like the base on the left. We have this base on the right. It's dotted because I can't quite see all of it. And again, this cross section in the middle, this dotted part in the middle, is to try to give it the idea that it is three-dimensional. So there's this three-dimensional shape on its side right now, and our goal is to find the volume of this. And what I would tell you is that the volume of this entire shape, again, what we are calling a cylinder, the term cylinder doesn't mean it has to have a perfect circular base. It just has a base parallel to a bottom base, and they are congruent to each other. So the volume of this one would be the area of the base, which we were given, times the height, which we were given, to get a total of 220. And labels are very significant to us. What would be the label for this one? So this was centimeters squared. This was centimeters. So our volume is going to be centimeters cubed, some kind of units cubed. This is centimeters cubed. All right, so here's where we come to picturing things three-dimensionally. I'm going to give you a couple of representations. The first one, let's make it a little bit smaller. I can spin this thing around a little bit. So you see like the region between this blue and this red. So that's just like on an XY axis. This is just like the gray part is just a plane. Let me back this up a little bit. That's just on a plane. And then we have this cross section right here. And I'm going to have this cross section start off by being like a semicircle. And I can move it from left to right. So I have all of these semicircles going from left to right where the cross section is in between those. And I can have it do as many of those semicircles as I want. So I'll drag it really far to the right. I have 9 semicircles. As I get more and more of those, do you see how that starts to make like a three-dimensional shape? I'm trying not to move it too much to make it crazy, but can you start to see a three-dimensional shape out of that? Instead of semicircles, I could make it equilateral triangles. It's a little bit harder to see. If you look straight on, you can see those as triangles with better. Or I can make them all squares. So there's just a few squares. But if I make a lot of squares, then it starts to get to be a three-dimensional shape. So this is one way to try to picture these, which is kind of difficult. I realize that. We're going to draw it as our third option. The second option is to look at something kind of like this. It says the base of a certain solid is a region enclosed by y equals square root of x, y equals 0, and x equals 4. Every cross section perpendicular to the x-axis is a semicircle with its diameter across the base. So this visual is a little different than the first one. This is a different equation. But what I want you to see is, on the paper, can you see the y equals square root of x graph? See that? And then it says perpendicular to the x-axis. Here's the x-axis. We have this distance, and then it's a cross-section for a semicircle. Perpendicular to the x-axis, we have a semicircle. So we could draw in even more of those to get more of those semicircles in there. And then we're looking at what's attempting to be a three-dimensional shape. So I think this particular one gives me a much better idea of what I'm talking about here. Our goal is to find the volume of this. What kind of shape is this? I don't know what I would call it. I would just describe it the way it was described there. We're going to try to draw this as best we can. So we're trying to make a three-dimensional shape on two-dimensional paper. So I have my x-axis, my y-axis. Y equals the square root of x. Looks something kind of like that. y equals square root of x. Where's y equals 0 at? What does y equals 0 look like? Horizontal line at the x-axis. So here is y equals 0. And x equals 4 is what kind of a graph? Vertical line. So here's x equals 4. There's another one of our parts. And so we have this as our region. I'm going to color it for right now. We have this orange region. And it says that we are supposed to get a solid, a three-dimensional shape, so that every cross-section perpendicular to the x-axis is a semicircle. I'm going to start, let me see, I'll go to about black. I'll start right here. So here is a cross-section perpendicular to the x-axis. Right, my segment here is perpendicular to this x-axis. I'm going from top to bottom. And this is supposed to be the diameter of a semicircle. So here is my base. There's my semicircle. And that's my first one. Now I'm going to move to the right and draw another one. So from here, I'm going to start drawing it. But because it's behind, I might need to dot a little bit. And there's a semicircle. These are going to start overlapping with each other. I'll hold up my visual here again. Like if you look at this from an angle and from a side, you can see the entire first small one, right? But isn't the second one partially obscured? And the third one as well? And so when we try to draw those things three-dimensionally, we make them dotted. So the next one, I'll drop it down. It starts to get dotted, and then there's my semicircle. Next one, I will draw it down. There's a little bit dotted behind. Then there's my next semicircle. Draw it down, dotted, semicircle. Next one, dotted, semicircle. Can you start to see that in 3 dimensions? Some of us have a really good artistic side to us. Some of us can really see things 3-dimensionally. Some of us struggle with that. But there is my 3-dimensional solid, which is trying to look like that actual paper version that I showed you as well. So we get that 3-dimensional solid, and the goal is to find the volume of that. Volume equals. In this representation, I have 1, 2, 3, 4, 5, 6, 7, 8 of those semicircles. In actuality, how many semicircles should there be? Infinite. That's where we're going to have to use an integral, which is a summation. It's going to add up all of those together. I'm just going to focus on one of them, and it doesn't matter which one. I'll just pick one of these here in the middle. I want to think about that actual semicircle. To find the volume of it, it's going to be the area of the base times its thickness. Kind of like I did over here. The area of this kidney shape was given to be 22, and then we multiplied by the entire thickness. We need to figure out the area of just that semicircle. In general, is this length from here to there, and I'll make it a little darker in red, is this length the radius of the semicircle? It's the diameter, right? So whatever this red length is, we're going to have to divide it by 2. This is one of the points on the graph, x, comma, y. What does this red length stand for, the x value or the y value? It's the y value. So the diameter of this semicircle is y. And if I want the area of the semicircle, what are you going to have to do with the y? Divide it by 2 because that's the radius. Then what? Multiply by pi squared, right? Pi times the radius squared. This would be the area of that one semicircle. But again, it's not actually just a semicircle. It's actually it has a little bit of thickness to it. It's actually going to be what we're going to call a cylinder. What is the thickness of this one? And here's the question that is going to determine a lot of things in our integral. How thick is this thing? Not very thick at all. Is the thickness from side to side or top to bottom? Side to side. What do you think we're going to call the thickness of this? dx. Here's one of those semicircles I'm talking about. The thickness of this one green one right here is side to side. That really thin thickness is in terms of x, so it is a dx. So the volume of any one of those semicircular cylinders is going to be the area times the thickness. Now, this is the area of one of those semicircles, but what do you want this in terms of? X, because it's a dx. Oh no, this is in terms of y. Well, let's go back up here, and here is our big substitution. We were told that this equation was y equals square root of x. So yes, this point is x comma y, but since y is equal to square root of x, I can go down here and make a substitution. Pi times, not y, but square root of x, because y is equal to the square root of x, over 2 squared. I put square root of x in for y. So now if we square this, pi is still pi. What is the square root of x squared? Just x, right? And then over 2 would be 4. So then the area of this semicircle, or any of those semicircles, is going to be pi x over 4. This integrand and what we're integrating with respect to represent the volume of any one of those. The area of the semicircle times its super thin thickness. What else does this integral need? Bounds. Bounds in terms of x. Can you go back and find them? What is the lower bound? From what x value? What is x value? 0. And the right bound? 4. Now, I'm realizing I made a mistake here. This isn't actually the area of the semicircle, is it? Did you catch that? What do we still have to do to this? Divide by 2, right? This would have been if it was the area of an entire circle. So we have to say divided by 2, which is going to make that actually into an 8 then. So sorry for that. That should have an 8 underneath it. The reason why we're doing a semicircle isn't to make it more complicated, but think about, we have a flat base right here. Could you put a semicircle on this flat base? Absolutely. Could you put a circle on this flat base? It's going to roll around. It's not going to sit on it correctly. So that's why we're doing like this flat base semicircle rather than a nice circle, which is why we're having to do this divided by 2. The hardest thing here is visualizing. Second hardest thing is trying to figure out the formula. This is your first time seeing it, so it can be kind of overwhelming at first. You will get better at these, I promise you that. Now, the easiest part is to integrate. Integral from 0 to 4 of pi over 8 x dx. What is pi over 8, basically? It's not a variable. What is it? It's a constant. What can we do with constants? Do I want to keep that on the inside? Not really. So push that pi over 8 out front. pi over 8. What is the integral of x dx? One half x squared. It's going from 0 to 4. And now let's plug it in. So pi over 8 times 4 squared times 1/2 is 8, minus 1/2 0 squared. Subtract, multiply. What is the volume of the shape? Pi. Pi units cubed, but we weren't given any labels, so we don't have to put the units cubed in there.